So now I can start recording. That makes it real. All right, happy Thursday. It's lovely 71-degree Thursday in the middle of November. Tomorrow's high, 31 degrees instead, of course. So I'm celebrating by wearing my shorts and sandals for probably the last time this fall, but you got to do what you can. So I've heard folks talking about courses and for next semester, just in case you haven't seen it yet. There is an advanced version of longitudinal models being offered at the same time in the same place next semester, and it is designed to follow directly where we leave off this semester. So those of you who have made it through this point, of course, would be well prepared. Anyone who's had the same type of coursework elsewhere would also be prepared, but folks who have not had anything longitudinal would not be advised to step into the advanced course because, as you all know, there's a lot, right? A lot of vocabulary, a lot of notation, a lot of concepts. And so it's hopefully designed to get into the most modern updates in terms of what people are doing with longitudinal models and hopefully give you a chance to do some practice with real data as well. So once you know how to make the numbers come out in SAS, data, or R, and you know how to interpret them, then you're ready to be turned loose with your own data and hopefully make some interesting research out of that. So if anyone has questions about that class or any other class for that matter, I'm happy to talk to you. If you're interested in taking more coursework but aren't sure what would be most useful to you, I'm happy to chat with you individually about that. So we have a new topic for today, time invariant predictors. Finally, right? We're getting into the part where we get to start testing hypotheses about how to predict change and fluctuation over time with variables besides time. So unless anyone has other questions or things they want to review, I can just dive right in. We ready for this? Yeah. So concepts first, then we get into the nitty-gritty application work. There we go. So the first thing, though, I have to start with kind of a bummer note, because I want you to be aware of what is going to happen to any predictors that are missing when we're using this kind of univariate estimation approach. It's not good news, I'll tell you that. So that's the first topic here. So missing data is a problem in research broadly construed. It's particularly a problem in longitudinal studies in which not everybody necessarily is going to come back for every occasion. So we can have missingness within occasion. Maybe you didn't answer every question or complete every task that was asked of you. You can have differential attrition, so monotonic dropout, meaning that once you're gone, you stay gone, you don't come back. Measurements at different intervals can also be considered missing data to some extent. So if somebody comes at occasion 2.6 rather than 2, you can think of their occasion 2 score as a type of missing data. Then there's planned missing data, which, yes, that is a thing. It is possible to deliberately not have everybody complete every measure so that people can have less of a burden in terms of what's expected of them. It can be done, but it has to be done very carefully. So that is another potential source of missingness. And often at the beginning of studies, there's a form of missingness that isn't necessarily recognized as directly. So selection bias, like who is available to be in your study? That's kind of like a type of missing data if you think about relative to everybody you might potentially want to study, who do you get? Who's available to sign up? In the case of the aging studies that I used to do, who is still alive and physically and mentally capable to participate in research? So missing data happens in all different kinds of forms. The goal of any missing data handling approach is to recover what the answers would have been if the data were complete. The goal is not to recover the missing values themselves. The goal is to come to the right conclusions. So not every approach to dealing with missing data involves filling in values. It isn't necessary. That's only one strategy. The methods that we do use to do analyses when we have some degree of incomplete data require assumptions about the mechanisms that are generating the missingness, as well as the variables distributions, if we are then to try to make use of all available data. So what not to do is a short list. Never, ever, ever, ever fill in one value and call it good. So there's a lot of different ways in which this is labeled. Single mean replacement is one thing, so that, for instance, there's a box you can check in SPSS to just fill in the mean for any missing values. A conditional mean from a regression equation, that's a different box that you can check. So you can have, what would y be if I predict it with all these other x's, and it will fill in a value. Can you guess why it's never, ever, never, ever? What happens if you just fill in a number as if it's a real number? Any thoughts? It's not going to bias the mean or the regression line, because you're filling in what the prediction would be. But what would potentially be distorted?
Standard error?
Yeah, variance. Right? If we fill in a perfectly predicted value, it's perfectly predicted. So we're not going to have as much residual variance as we would if there were real data in which it's not going to be perfectly predicted. And if we don't have enough residual variance, then we don't have enough standard error. And if we don't have enough standard error, we don't have enough p-value. So everything looks too good, basically, if you fill in values as if they were real. And I have preferably not, because sometimes you're stuck with this, but hopefully not, is listwise deletion of all people. So if you have somebody in a longitudinal analysis and they are missing one of the occasions, we don't want to drop the other occasions that they do have, although in some circumstances that is what's going to happen. What to do instead is a continually developing area of research. So it used to be that sort of the state of the art, and there was a 2002 Psych Methods paper that's very well cited, I think it was literally called The State of the Art with respect to missing data, is FIML, as it is pronounced, or multiple imputation. So FIML stands for full information maximum likelihood. That is what we've been using this whole semester, and that is pretty much the default when it comes to maximum likelihood estimation across packages right now. The term full information means that you are using all of the original data to estimate the model parameters and not a summary. So in contrast, what would be not full information but limited information would be if you provided your software package with the means of a set of variables, the variances, and the covariances. Believe it or not, it could still do multi-level modeling on just that much information. It could still do structural equation modeling on just that much information. But that would be considered a limited information approach because it's starting with a summary and then trying to estimate the model parameters that best recreate that summary. The summary never knows what it doesn't have. The summary doesn't know what's missing from it. And so that's where the problems start to come in. By the way, residual maximum likelihood is also full information. It's just not called FREML for some reason, even though it should be. So REML is FREML. So the multiple imputation side of this is something that honestly I've never done in a real analysis in my life. But the logic of multiple imputation, very briefly, is filling in the missing data. So you build what is known as a missingness model in which every variable that has some degree of missingness is predicted by other variables in the data set, as many as you want. And it does create a predicted value for each missing data point, but then it adds error to it. That's the critical part. It draws error from some kind of distribution and adds an E or an R, whatever notation you want to use, to that individual value. Then you do that a bunch of times. So back when computing was not as easy as it was, like 5 times might be what you did, 10 times. Now you could do it, hundreds or thousands of times in a second. But the key distinction is that you're not imputing or creating missing values that are perfect. You're creating the perfect ones and then adding error. And each time you go through and do this to the same data set, you're literally creating different versions of complete data, each one with a randomly drawn error term to all the missing data parts. To get an analysis result then, you would have to analyze every single completed data set with the same model, then use particular rules to combine the estimates, where the estimate standard errors are then created not only out of the average standard error for each data set, but also a contribution from how different the results are across data sets. So variability across the standard errors in addition to the variability that the standard error represents. So those are called Rubin's rules, I think. It is not correct, if you've ever seen this, to average the data sets all back together again, because then you would end up right back at the same place as single imputation, where you've averaged out all the errors, and then everything looks too good. So that's what multiple imputation is. If you use the same information in your analysis as you use in the missingness prediction model, you will get the same answers. Asymptotically, these things are equivalent. So my standard approach to having missing information and still being able to do an analysis, I should say, is FIML. Because you don't have to go through the process of filling in the values and all the extra legwork that's involved with respect to averaging the results. It's also easier, I think, in a lot of cases to extend it into variables that are not normally distributed. However, both of these things, and I will add Bayes to the list too, because Bayesian approaches to missing data also involve kind of filling in things and then running repeated analyses. Both of these assume something known as missing at random, or the acronym is MAR. So here is the classic set of labels that people characterize missing data with. There are missing completely at random, MCAR, missing at random, or missing not at random, or not missing at random. The not gets stuck either in the second place or the first place, depending on who you read. So missing completely at random is exactly what it sounds like. There's no reason why you don't have the information. It's unrelated to what they would have said, and the fact that it's missing is unrelated to anything else in your data set. This is the only one that is potentially testable empirically. If you look at an outcome and you categorize that outcome into a new binary variable where 1 is its missing and 0 is its present, you can then use that as a grouping variable and look at differences across all the other things that you have in your data set. Like, is this person characteristic more likely to have missing data? Is this type of person? Is this type of occasion? Like, whatever information you have. And if you find that anything in your data set is related to the probability of missingness, then by definition, it's not MCAR. It's not completely at random because it has something to do with information you have. Missing at random is the one that we assume. And this is trickier to explain, but basically what it means is that once you control for or condition on the information you do have, then it's random. So the fact that it's missing is related to what they would have said, but what they would have said goes along with everything else they said. So there's no new information essentially that you wouldn't already have about the person once you take into account what you do have. Missing at random is not testable in any way, shape, or form. And that makes it one of the favorite things that reviewer 2 gets to complain about. Because you state, I use blah, blah, blah approach to my missing data, assuming missing at random, and they're like, how do you know? I don't know. But what you can say is, well, I put this variable in the analysis and this variable in the analysis, and previous research has suggested that these things are related to the phenomenon I'm studying, as well as the potential for attrition. So anything that you have that would help predict why someone didn't come back and what they would have said goes in the model as a control. So if you're studying children and you know that certain children moved out of district, and that's why you don't have any more data for them, that goes in the model. Because a child moving away is very different than a child like dropping out of school, period. So if you have that distinction and you know that, you can put that in the model. So the only way to argue that missing at random is plausible is theoretically, which is very dissatisfying, but ultimately that's what everyone assumes. Not missing at random is probably more likely, but nobody wants this because it means that basically everything you do is some kind of wrong. You don't have the information you need. The fact that it's missing is related to what they would have said. So if you're asking questions about substance abuse or sexual behavior or anything else that people might feel uncomfortable sharing and they don't answer the question based on what they would have told you, that's missing, not at random. So in those sorts of situations, what you would have to do is essentially specify like a reason why it would be missing and build that into the model as a selection process. So those can be more complicated. You might have to try out different scenarios and make, again, theoretical arguments as to which one might be more likely. You would also ideally want to see that the primary conclusions that you draw stay the same if you try out different mechanisms of missingness. So for more information about this, there is a book on your reading list for this semester. It's Craig Ender's first edition of Applied Missing Data Analysis, and I assign chapters 3 through 5, as I do in every single one of my classes that uses maximum likelihood, because his explanation of it is the best. He just came out with the second edition of this book that has a whole bunch of new stuff. I just listened to a podcast the other day, the Quantitude podcast, where he was a guest, and he said that he basically just scrapped the entire text that he had and started over in writing this book because there was so much new stuff that he wanted to be able to say, and it didn't make sense to fit it into his old framework. So that's definitely one that I'm going to get and would recommend if you're interested in reading more about how to address missing data in the context of a whole bunch of new other types of models. So now here's the bad news. I have often read at the beginning of results sections statements such as multi-level models handle dependency, or multi-level models handle missing data. Handle is a word that people use when they don't know what they're talking about. What is going to happen is that any row in your data set that is incomplete with respect to the predictors and outcomes in your model is getting dropped. If that's handling it, then I'd hate to see what not handling it looks like, because that's bad. It's because the univariate type of model that we have, and to me it's univariate because there's one column that holds all the y's. Y is the only thing that's in the likelihood. So the predictors contribute in as much as they generate predicted y's, but the predictors are not in the likelihood otherwise. So if you can't generate a predicted y, if you have missing data, then you can't keep it. So because this is a univariate conditional likelihood where we're only focusing on y's distribution, we can't have missing y's to be created, and we can't have missing predictors as a result. So it is going to delete incomplete cases, occasions within a person, and potentially whole persons, depending on your pattern of missingness. So why haven't we talked about this up to this point is because odds are good if you have an outcome at a given occasion, you have the time at that occasion too. So we would have only talked about missing outcomes at this point because time is a measured predictor, we would probably have that. But other measured predictors may not be complete. And your sample size may change across models for that reason. So if you are committed to working within this univariate framework and you don't have a lot of missing data, then it would probably make the most sense to filter your data set based on complete cases of all the variables that are eventually going to end up in the analysis and pre-select your sample accordingly. Otherwise, you can end up in inconsistent results where if I use this sample, I get this conclusion, but if I use this sample, which is reduced because of this other predictor, then this other predictor is no longer significant. Like you can get inconsistencies because of differences in people. The other thing that can get tricky is that log likelihood is the sum of the heights, right? Each person has a value that describes the height of their y's. So if some people or some occasions don't get included, then those sums are not comparable across models. So any model comparison involving -2 log likelihood, AIC or BIC, are only comparable if the sample is exactly the same. Kicking out cases is going to reduce your power. There's no way around that. So just as an example here, if I start with a wide data format, which is this is what it would look like at the top here if we were doing a repeated measures analysis of variance, sort of your classic least squares approach, this type of wide data structure is also what is used in structural equation modeling. To fit multi-level models in which the y's all need to be in one column to be predicted, we would transpose or reshape this wide data into long data, where in wide data it's 1 row per person per level 2 unit, and in long data it's 1 row per level 1 unit instead. So 1 row per occasion in this case. So if we look at this particular pattern, I want you to tell me which rows are going to get included in each of these models. So if I have a model with just time and my dependent variable, which rows get included here? Try not to look at the answers in front of you.
Everything except for 7?
Yeah, everything except 7 in this case. How about if I add this time varying predictor along with time and the dependent measure?
Oh.
Yeah, not 7, not 6, not 4. Now what if I add a person level predictor, a level 2 predictor, time invariant predictor, that's what we're focusing on the rest of the semester. Now what gets used?
1, 2, 3.
Yeah, the second person is gone. So yeah, it is back to listwise deletion if you're missing person level predictors, because they will be missing the whole time. It's not good, but it is what's going to happen, and I wanted you to be prepared for that. And then the last one, if I put in everything, only rows 1 to 3. So given that this is what happens, what do we then have to assume about any missing data that results in cases being dropped? So any cases that are missing model predictors or outcomes are not going to be part of the likelihood. This is very bad, or it's bad at least, for time or time varying predictors. And I actually sent Craig Enders an email about this a long time ago saying, what would you call that? And he landed on sort of missing at random. So I have missing at random-ish. And the logic is because if it's a time varying predictor that you're missing, you may have it for some of a person's occasions. So to the extent that what they would have said is consistent for the missing one, you do have some information about it, and it's kind of missing at random-ish. But the ish is necessary to clarify that X is not in the likelihood, so we can't really say it properly as missing at random. But anybody who's missing a time invariant person level variable is getting dropped, listwise deletion, and anything with listwise deletion is missing completely at random. So if you have a lot of missing data, then this approach that we've been using this whole semester is not going to be viable in terms of estimation. Because not only are you limiting your power by dropping people, you're also changing your inference. Like, who is left? Like, I can now make inferences about a population of people that all answered these questions, or, that provided me with this type of information, and it may not be the population you had intended. So what to do instead? The good news. It boils down really to software differences, not conceptual differences. Every single thing that you've learned about longitudinal analysis still applies. If you take the model that you want to fit and you phrase it as a structural equation model, or as a multi-level structural equation model, or as a Bayesian analysis, all the same ideas apply. The difference is in what is assumed or required for missing observations. So if you're missing a lot of predictors to the point where deleting them is not going to be viable for you, the easiest way to solve the problem is to bring the predictor into a joint likelihood. What that means is switching to software that has multivariate analysis capabilities, such as structural equation models or multi-level versions of those. Then you can ask it to pretend that a predictor is an outcome. You ask it to estimate the predictor's mean, variance, and potentially its covariance with other stuff. And that brings the predictor into the likelihood as if it were an outcome. Then you can have missing data under an assumption of missing at random, the same as the outcomes. The only catch is that you are then having to make distributional assumptions about the predictor the same as you do for any outcome. Normally, there are no distributional assumptions about predictors. They can be whatever shape they want, right? They can be categories, they can be counts, they can have bimodal, whatever. Predictors can be anything they want. But when you turn it into an outcome, that's not true anymore. And to the extent that you have a lot of missing data on a predictor and a predictor that's not normally distributed, trying to pretend like it is may not lead you into the right place. So in M+, for instance, the only way to turn a predictor into an outcome and have it be not normally distributed is to literally make it predicted by something else. So if I have a binary predictor, let's say group membership, I'm in group A or B and it's missing, I could tell a program, hey, treat this as a binary outcome, predict it with a logit, say it has a Bernoulli distribution. But then you would literally have to predict it with something else in the data set to make that work in the software. So you can't get everything for free, basically. This is the easiest trick in terms of bringing predictors into the likelihood, but they do have the distributional assumptions. What is often not realized is that the same is true in multiple imputation. Any imputation model to fill in the missing values does so under a distributional assumption. And if that's not accurate, then your conclusions can't be accurate. Multiple imputation in a multi-level modeling context is especially tricky, because in order for your eventual analysis model to be accurate, everything that you would eventually want to put in your analysis model has to go in the imputation model too. That means interaction terms, random slopes, R-matrix covariances, everything that you might want to try has to be involved in imputing the data. And in most cases, in terms of what the software programs are going to assume, is that everything is multivariate normal, and interaction terms cannot be. Random slopes introduce heterogeneity of variance, so it would have to be able to allow for that. So this is an active area of research, what to do, and I would recommend that book, Applied Missing Data Analysis, 2nd edition. I'm looking forward to reading more about this kind of stuff. But I wanted to be upfront with respect to what is going to happen when we start putting predictors in. Any row that is incomplete gets dropped. Okay, I've done a lot of talking so far. It's already 1 o'clock. Questions or comments? I once had an essay question that I used at the end of this class, which had a story problem of somebody who put a predictor in a model, in a multi-level model. The predictor was non-significant, but the -2 log likelihood went down by 200. And the question was, how could that have happened? So I'll ask you this. How could that have happened? Predictor is non-significant according to the Wald test. So estimate divided by standard error treated as a t, that p-value was non-significant. But if you would have done a likelihood ratio test to compare -2 log likelihoods, it would have said it was way significant. How could that happen?
Yeah. The random effect for that predictor?
No, only a fixed effect was added to the model.
Well, I would guess if there are cases missing when you add that new variable,
That's it.
comparing the same model, really.
Yep, that's exactly it. Missing data is the answer. Because the sum across people is different if it's different set of people. It could also be the case if you were using REML instead and you try to do a likelihood ratio test on models with different fixed effects, but it shouldn't be that different. It's not comparable, but it's not off that much. So whenever you see a huge drop in log likelihood or -2 log likelihood, it's probably missing data, and you need to watch out for the change in sample size across models. So having missing predictors not screw everything up and kick people out is one of the reasons why someone would switch to use structural equation models to estimate longitudinal models. However, then you're stuck with regular flavor maximum likelihood, and then you're stuck without denominator degrees of freedom. So it's not a good solution for small samples in that case. So, yeah, you got to pick your battles sometimes. It's hard to get everything the optimal way. Sometimes we have to choose the least worst option as opposed to the best option. Have I bummed you out? Yeah, you can say it. It's okay. Everyone looks kind of bummed. Like I just ruined your day. I didn't mean to. But I wanted you to be aware of what's going to happen. Like, that's the thing. So I'm going to try to cheer you back up, okay? So what can we do with time invariant predictors? These are opportunities. Let's cast it that way. So independent variables, predictors, or covariates. I don't care what they are. Those three words all mean X to me. The difference is an interpretation. So the term independent variable as a predictor generally goes with the idea of an experimental design where the independent variable is something that's been manipulated. That's where that terminology comes from. So you would have independent variables as your X predictors instead of dependent variables as your Y outcomes. Predictor versus covariate is a subtler distinction, but predictor to me is the term that I use because I don't try to put myself in the shoes of the theorist who came up with the model. Covariates tend to be predictors someone else cares about who's not you. So a covariate is something that is controlled for before you put in the things you actually care about. At one point in time, the fact that the covariate was related to the outcome was noteworthy and publishable, but now everybody knows that, so we're just going to control for it. So whether you're thinking about your variables as a key independent variable like manipulation of treatment group, something you care about, which is a predictor, or something someone else cares about but you have to control for as a covariate, I don't care. Math don't care with respect to those things. That's an interpretation question. So by definition, a time invariant predictor is anything that does not change across time. So the sex that you were born with, for instance, as opposed to gender identity, which is more fluid. It may be something that you only measured once, and if so, you have to pretend it's invariant even if it's not. And that's where you get into a little bit of tricky territory with respect to how you talk about a variable. So for instance, if I were measuring adolescence, if I had a data set where it was, say, ages 12 to 18, and at the beginning of the study, I gave out a whole bunch of different questionnaires to the parents, and I never re-administered them, then I would have to talk about, parent attitudes or parenting strategies at age 12, because I don't have any information that would say they stayed consistent across time. So I'd want to limit my conclusions to the occasion that they were measured on. It can also be things that do change across time, but are perfectly correlated with time. So for instance, if I have your current grade level as a metric of time, then the grade level that you started at becomes a time invariant predictor to help differentiate cross-sectional differences in grades from longitudinal differences. So anything that is measured once or perfectly correlated with time is a time invariant predictor. So you will hear synonyms of level 2, between predictors, person level, person characteristics. All of those words mean the same thing. In terms of notation, they're all going to get an I subscript only. Can you guess why they don't get T's?
Because they do not change.
Because they
over
do
time.
not change, that's right. So T would be redundant or unnecessary. So that's one of the things that in notation for these models, subscripts become very useful for someone to immediately identify at what level of the model the predictor is measured. So anything that's a TI, I know is time varying, and anything that's an I is not time varying, is time invariant. Time constant is another thing people say. Time invariant is a bit of a mouthful. As with time and any predictor in any linear model in the history of the world, we center such that 0 means something. I will die on this hill. I taught the other class this, right? That expression? To say you're going to die on a hill, I will die on this hill. It means that I'm going to emphasize this and I'm not going to back down. I'm not going to let this one go. Centering predictors creates interpretations that are much more useful. It doesn't necessarily change the conclusions in every case, but it can sometimes. So I am in the habit, literally from the very first linear model I introduce in beginning regression class, every predictor gets centered so that 0 means something. If the predictor already has 0 as a meaningful value, like the number of times something happened to you, and 0 is a possibility, then leave it alone. 0 is meaningful. But if you have, say, a Likert scale of like 1 to 5 for something, 0 can't happen. So then all of your intercept and your intercept variances and everything else that would be conditional on 0 are not going to make any sense. As we will see with the examples that I have to show you, very quickly we will get into models that have 2- and 3-way interaction terms. Because if you want to ask, do people change differently as a function of this predictor? That's an interaction. It's the person predictor by time. Do people change differently in terms of their quadratic slope as a function of this predictor? That's a 3-way interaction of predictor by time by time. So especially when we have models with interaction terms, the simple effect of the slope for one of the variables in the interaction is going to be conditional on 0 for the other one. So that's yet another reason why we would want to pay attention to this. Continuous predictors, or quantitative predictors, as I tend to try to call them, the most common thing people do is center them at the mean of the variable. That's fine. But for variables that have a scale that is already meaningful, it might be more useful to pick a reference point that has some kind of absolute meaning, not just relative. So for instance, if I had something like years of education as a person-level covariate, right? I've been involved in a lot of research on children with specific language impairment, as an example, starting back from when I was a graduate student and I was helping with analyses for Mabel Rice and other folks at the University of Kansas, continuing that line of collaboration to today. One of the things that she always controls for is mother's education. Not fathers, mind you, mothers. That's also a whole nother layer of bones that I could potentially pick, but that's a covariate. And if it's measured in years, I could mean center education. So for instance, in one of the data sets I'm familiar with, the average number of years of education is 14.12. So if that were to be my reference point, that's a little weird because nobody wrote down 14.12. It's like my reference point, my sort of prototypical individual for the model would be somebody who went to 2 years of college and then dropped out in October. Like, is that what 14.12 would mean? Something like that? It's weird. So if I had something like education level, I might pick 12 years and say my reference person has a high school degree and talk about what happens as you move beyond that. In another sample, a lot of studies on aging adults, more often than not, at least in the literature that I was familiar with from the 90s and early aughts, the older adult sample are retired faculty and their spouses. That's who participates in cognitive aging research. So what do you think the average education level is in that kind of sample? A master's degree in most cases. If not, full up doctorate or JD or MD or, any of those other kinds. So if in my method section, I say, the reference person is someone who's average on education. In one sample, that could be somebody with a master's degree. In another sample, that could be somebody with a high school degree. And yet another sample could be someone with 8th grade education. So average is a relative thing that may not be as useful as an absolute number. So you don't have to pick the mean. You can, but you don't have to. For categories, somebody's got to be the 0. So my preference is some kind of dummy coding scheme where I have a zero group and then I have coding that reflects differences relative to the zero group. You can do effects coding. I don't like it, for the same reason that I don't like the mean as a centering point if no one's there. So if I have like a grouping variable and I want to look at differences between, say, group A and group B, and I code group A as -1 and I code group B as 1, then who's my intercept for?
0.
Hmm?
0?
0. Who's in group 0? Nobody. There's nobody in my sample that is in group 0. They're either in A or B, and A is -1 and B is 1. Further compounding that, the difference between -1 and 1 is how much? Let's see if you're listening. What's the difference between -1 and 1 in numbers? 2. And in all the time when we talk about slopes, do we talk about a 2-unit change? No, we talk about a 1-unit change. So the slope is twice as big as it should be. Yeah, or half as big? I always go the wrong way. It's not right, though. It's 2 instead of 1. So I would do plus or minus 0.5 to make it 1-unit change if I were going to do that.
Just to be sure, yeah. So in those cases, using the effect coding, we would have just one slope, not 2.
If it's 2 groups, you would have 1 slope, but if it's more than 2 groups, you'd have others.
Okay.
But that combination of plus or minus 1s creates an average that isn't anybody that you have. So talking about what would be expected for that person, like as a series of, say, simple effects, to me is just weird because that person doesn't exist. Plus the 2-unit change thing, like that's easy to screw stuff up then. So just to remind you, coding schemes that you might consider for categorical predictors. Here are 2 that I find to be most useful. Indicator coding versus sequential coding is what I have found these to be called in the textbook I use for intermediate. Indicator coding is probably better for nominal kinds of grouping variables where there's no ordering to it, whereas sequential coding is probably more useful for ordinal type variables. So either way, you would have one group designated as the reference. So I have that in green here, for instance. So group A in this coding scheme is the reference. And then my first contrast is going to differentiate B from A. The second one differentiates C from A. And the reason that it's interpreted that way is because group C is coded 0 here. So if you look at how these things would work, if this was the only column in the data set, or in the model, excuse me, A versus B, what would we get as a comparison if this was the only thing we put in? What would it actually be? Yeah, B versus A and C lumped together, right? Because A and C are both 0. And so to fix that then, since A and C are lumped together, we pull them apart with the second contrast. Then we get A versus B and A versus C. Likewise, if I only had A versus C in the model, I'd be lumping together A and B, and they get pulled apart by this one. So when they're all put together, they have the correct interpretations. So if it's 3 distinct groups, for instance, where there's no ordering to it, this would tell you how B differs from A, how C differs from A, and then what if you wanted to know if B and C are different?
Linear combination.
Linear combination. Yeah, the model doesn't tell it to you directly, but it tells it to you indirectly. So we would subtract the slope for A versus C, and then subtract from it A versus B, and that gets us the missing contrast. So that'll be one of the things that I show you in the example. An alternative then is sequential coding. This is used in kind of like a stair-step kind of thing for ordinal variables. So the difference in the coding is that whichever level is denoted as the alternative group doesn't go back to 0. It stays at 1. So when all 4 of these contrasts are in the model, then the first one tells how 2 is different than 1, 3 is different than 2, 4 is different than 3, and 5 is different than 4. So if you have a variable like strongly disagree, disagree, neutral, agree, strongly agree, this would tell you how the outcome differs as you move up each adjacent category. which to me is more useful than knowing, say, if strongly agree differs from strongly disagree, because those are like, very far away relative to the coding. So these are just two examples of what one can do for categorical predictors. Ultimately, it's up to you to figure out what coding scheme best maps onto what you want to know. Question? No? Okay, here, you're just hand fleeing.
Yeah.
You still with me?
Yes.
Okay. All right, so what can these predictors do? In the model for the means first, if I have within person change, they adjust the growth curve. That's what they're for. They help answer the question, why do people start out differently? Why do they change differently? Or if time zero is at the end, why do they end up differently? And why did they change differently to get to that point? So here's one possibility. If I put in a main effect of a time invariant predictor, so I have x as a generic sub I, because each person has one value of it, and I do not put in an interaction with time, then this is the type of prediction that it could make. Let's say that I have x as a grouping variable, or maybe just a continuous variable where these are prototypical values of like high x and low x. Then we would talk about how x has shifted the intercept specifically. And without an interaction with time, the model predicts that same intercept shift to be constant across all the observations. So a main effect of a time invariant predictor is an intercept effect specifically. If I put in an interaction then, I have main effect of x question mark. So the idea of allowing x by time to have its own new fixed effect then allows different trajectories. So I'm saying that the time slope can differ between low x people and high x people, for instance, or group A or group B, or however you want to think about it. Now I have main effect of x question mark because what would determine in this model whether or not I have a significant main effect of x or not? Because once you have x by time, the x part is conditional on something, right? When you have an interaction term, the other variable is conditional on its interacting predictor equals 0. So what would I have to know in order to interpret the main effect of x? Is it this intercept difference? This one? That one? Which one am I going to get? Because now it matters, right? The intercept difference is not constant. Am I going to get this one, this one, this one, or this one? How do I know?
For me, that depends on your design, but for
Design
example,
matrix. It depends on my design matrix, I would say.
Why?
Why? Because it has to do with where is 0,
Yeah.
right? So if time 0 is this first dot, I may not have a main effect, right? Because at this point, there is no real intercept shift. If time 0 is at the end, then maybe I do. Or if time 0 is at the middle. That's a choice too. So I would say, yes, if we work backwards from the logic, the main effect of x, once we have x by time in the model, is the effect specifically at time 0. Your design then informs where that should be. Like, where is that most useful? Do you want to know if x is related to intercept differences at the beginning, intercept differences in the middle, or intercept differences at the end? Now let's say that x is a randomized variable. People are randomly assigned into conditions of x. Do I want to have a significant main effect of x at time 0? If it's at the beginning?
No.
No, because that means I screwed up my randomization, right? Like, they should be the same. So you might have a model where time 0 is at the beginning just to make the point that there were no baseline differences on this thing that you should have made equal across people.
Lisa, I have a question.
Hit me.
I think this might be more related to piecewise models, but when you, and I joined a little late, so I apologize if this isn't exactly on topic, but if you change where the intercept is, like where 0 is, kind of like in the homework, the 7th occasion is the intercept, can you still include like a quadratic effect taking the log of that? Because you can't take logs of negative numbers. So like, it would go backwards. So what would you do in that case?
Yeah, you would, I don't know that you would have full flexibility in where you put 0 because of that constraint. So you might have to make sure that time 0 is at the beginning. That way the quadratic is defined everywhere else. But the good news is that you can get what the effect of x would have been at any other occasion as a linear combination of the fixed effects. Another way of saying that is that the simple slope of x, when it's part of an interaction of x by time, the simple slope of x you can get here, 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 or here. You can ask for whichever one you want, even if it's not the one that's directly provided by the model. Or you could have a picture with an interaction where there's both. So this would be where people who are higher on x were already higher on y to start with, and they grew more. So point of the story, the role of time invariant predictors is to moderate the growth curve. And any aspect of the growth curve that has individual differences is an ideal candidate for moderation. In a fluctuation model where time isn't relevant, you might just have an adjustment of the intercept. So if time's not part of the model, then these might be your only choices with respect to what x can do in the model for the means specifically. Let me skip a slide for a second because I want to make this point. Level 2 predictors cannot have random effects. So when we add level 2 predictors, they are only going to have fixed effects. The reason for that, if I have a variable like time, each person has a different value of time at each occasion. I can draw a slope that's separate for each person through their own points. And people can have different slopes as a result, so long as I have how many occasions, by the way? 3, at least. 2 would be a random slope for time is the same thing as the residual. They're not separable at that point. So as long as I've got 3 occasions, I can draw separate slopes for separate folks. For group, as a generic idea of any level 2 predictor, by definition, if the predictor is a level 2 predictor, it's the same across time. So each person would have like 4 dots that are exactly in the same spot, and you cannot make a line through 1 dot. So any level 2 predictor's effect can only be fixed. There is nothing for it to vary over in a 2-level model. ... But what if these were nested data? What if I were following children from different schools over time?
We will have more data.
Then we would have, well, so if this was like some child level predictor, let's say this is gender, for instance, and I've got boys and girls, the fixed effect would describe a gender difference on average. But if I have observed boys and girls in different schools, then do you think the gender effect might differ across schools?
Yeah.
It could, certainly. And so then we would have a random slope for that person level predictor across level 3. In the same way that time is random across people.
Each additional level is an added dimension, or related like quadratic or cubic. Or is that, am I overcomplicating it?
Dimension maybe, but it's an orthogonal dimension.
Okay.
So as a general principle, any predictor that is measured at the highest level of sampling can only have a fixed effect, not a random effect. Any predictor that is measured at a lower level of sampling can have a fixed effect at its level and a random effect over any higher level. So in that 3-level example, if I had time within child within school, then individually varying time slopes could happen across the kids, right? But do you think that some schools might have more growth in their kids than other schools? Then the time slopes could be random over schools, too. So a level 1 predictor can be random over 2 or 3. A level 2 predictor can be random over 3. But at the top level, there's nothing above it to be random over. So this makes our level 2 unit comparatively easier, because not only is the predictor measured at a single level, but if it's at the highest level, it can only have fixed effects.
This
Yeah.
is the same with quantitative predictors at level 2?
Yeah, doesn't matter what kind.
Okay.
Yep. So you can think of these as distinct kinds of people, or this is high and this is low. Typically, to make these sorts of descriptive plots, we would pick prototypical values of a quantitative predictor. So we might show like the mean and plus or minus 1 standard deviation and show what the growth curve would look like at that point, that point, that point, kind of thing. You don't have to cut them up, though, certainly. Any kind of predictor you want. All right, 130. So to plant a seed, one of the things that I really want to cover next semester, because they're just so darn cool, is a use of time invariant predictors in the model for the variance. So this is the idea of predicting differential variability across people. The name for this is location scale models. And just to give you an example of what this would be, let's say that I had gender differences as a predictor in my model. So let's say I'm looking at growth in boys and girls. I can put in gender as a main effect and give it a fixed effect. That would allow outcome differences between boys and girls. I can put in gender by time as another fixed effect, and that would allow boys and girls to have different slopes. But beyond that, what if I wanted to know if girls were more variable than boys? The idea of greater or lesser amounts of individual differences in one group versus another. Could I do that?
Yeah. Interaction effect?
It's not an interaction effect per se. It is basically taking the variance component for the intercept and potentially for the slope and turning that amount of variance into another kind of outcome. So in a simplest case, what this would involve is allowing different G matrices by gender. So that's easy to do in SAS and Stata. It's group equals on the random line or in the random section. And that would, then we could do a likelihood ratio test to see if allowing different G matrices by group improves model fit. And we could look at each piece of the G matrix to see if it's different across groups. Where that might show up in intervention designs, for instance, the control group might turn out to not only be lower than the intervention group, but they might be more homogeneous. Because if you give a treatment to a whole bunch of different people, it may differ in its effectiveness more in that treatment group, and that spreads people out. Thinking about behavior change, there's a lot of contexts in which the goal is not to make somebody have more or less, but to have them to be more consistent. So something like monitoring glucose in diabetics, We want the glucose to not spike so extremely. We want it to be much more even-keeled. So the end goal of a research study or a treatment process might be less variability. And in that case, we're talking about the level 1 model. So the E's for each person. If you picture someone's trajectory for something like glucose, there may be some people that have a trajectory that looks like this, like it's all over the place, and some people that have a relatively more flat. So the extent to which each person has different amounts of variance over time, that is another kind of prediction that we can make with these types of models. So I put a couple links in here if you're interested. This is a YouTube video that I found by Don Hedeker, who is one of my personal heroes and basically the grandfather of these models. I also wrote a paper with a former student that is a annual review of psychology paper, and the second half of it is all about these models, so that would be a relatively gentle introduction. Estimation used to be a lot harder. It still kind of is, but there's more ways to do it, and once again, I hope this is one of the things that I can show you more about next semester, because it's really cool. Differences in variability is another way time-invariant predictors can contribute to the model. So anyone else think this is cool? Give you ideas? So things like improving consistency of daily exercise, improving consistency of medication adherence. Like there's a lot of situations where the goal is to reduce variability, not necessarily to change an amount. So you can do that with these. Yes, question?
Yeah, so could this be used in like a diff, with diff applications to see like if, variation is homogeneous or heterogeneous between like group membership?
So yes, that you can think of this that way if you allow variability in a latent trait to differ by group. That's kind of heading in this direction.
Okay.
You could imagine theta variance varying continuously as a function of a quantitative predictor too, which is even more in this direction. But yeah, this is one of those like model assumption things, right? Like we always assume heterogeneity of variance across people. Well, what if we don't have to? Like, what if that's not even plausible? We don't have to. Yeah, 136. Okay, do you want to see an equation at 136 on a Thursday? Can you handle it? Maybe one? Sometimes it's easier than concepts. So this is a jumping off point. So just to orient us, what I put up here is a random quadratic time unconditional model. So this phrase unconditional here, the idea, you're shaking your head, no, it's not unconditional?
No, it's like no predictor.
No predictors, that's right. So it's not truly unconditional, it's not empty, but there's nothing else in this but time. So why would this matter? This model is our new baseline for comparing the effects of predictors, because we have fixed intercepts and random intercepts, fixed linear slopes and random linear slopes, and fixed quadratics and random quadratics. So these U variances are unconditional, meaning they are not predicted by anything. This is as much variability as there is in the data. So it's kind of like a new empty model with respect to how people differ from each other. People differ in their intercept, they differ in their time zero linear slopes, and they differ in their quadratic slopes. We don't know anything about why yet. We just know that they do. So these numbers, the variance of the U's, the variance of the U0s, 1s, and 2s, these are what we want to see go down as we add predictors. So any analysis would logically start as like this model is the baseline against which we would judge the effects of predictors. So let's say that we wanted to add education as a time invariant predictor. Given that people differ from each other in 3 ways, there's 3 different ways that education can enter this model as a fixed effect. As a main effect, it moderates the intercept. As an effect of education on linear time. Another way of saying that is an education by time interaction as another fixed effect. Then education would moderate the linear time slope. Likewise, education on quadratic time, or education by time squared. So words on the slide to describe what's happening next here in the equation. So now the subscripts start to make a little bit more sense with respect to the zeros and ones here. To remind you, the first number in each of the subscripts refers to what beta we're talking about at level 1. So anything that's predicting beta 0 starts with the 0 in every place. Anything predicting beta 1 starts with a 1. Anything predicting beta 2 starts with a 2. The second number is within that beta equation, what is the order of the predictor? Where the fixed effect alone is the 0, the first predictor of beta 0 is 01, the first predictor of beta 1 is 11, the first predictor of beta 2 is 21. In the U's, they get an I in the second spot because they're varying across people. But the reds, the fixed effects, do not have I's because they are fixed constants, estimated by the data, but they apply to everybody. If I had a second person level predictor, let's say age or something, and I put it right here where my mouse is, what subscript would it get?
0, 2,
02. And if I added another one,
0, 4.
03, 04. And if I had age by time, what subscript would it get right here?
12.
12. Yeah, 1, 2 is where I was going with that. The 12 works, yeah. And down here, a second one would be 2, 2. So you can kind of think of it like a grid. The first number is which beta, the second number is the order within that beta equation. So if we do the first line then, beta 0 is how each person gets its own intercept. It is a placeholder defined by fixed and random effects. So I have education in which the 0 value is 12 years. So consequently, my fixed intercept here is conditional on all predictors being 0, which means time 0 and education 0. So I would say that gamma 0, 0 is the expected outcome when time is 0 and education is at 12. So time 0 could be the beginning of the study, could be the end of the study, it's up to you. Then gamma 01 is the main effect of education, and it is the change in the intercept for a 1-unit change in education. So to the extent that people who have more education have higher outcomes, that would show up as a positive gamma 01. To the extent that people with higher education have lower outcomes, this would be a negative. Then U0 is what's left. So I'm going to still call this a random intercept, but I'm going to call it a leftover random intercept. Because this is all the reasons why people still need their own intercepts controlling for education. So these are all the differences among high school graduates. These are all the differences among college graduates, like all of it. With conditioning on education, these are the remaining differences. Because of this idea that this is left over after predicted, some folks will call this a level 2 residual. Residual meaning like discrepancy or leftover, but I am reserving the term residual for level 1. I'm not going to do that to you. So it's leftover random effects as far as I'm concerned. So if education matters in predicting the intercept, what should happen to the variability of U0 relative to the previous model? Should be reduced. So this is where if I wanted to compare how much U0 variance did I have before to what I have now, that's pseudo R square. So we would take the U0 variance from the baseline model with no predictors, minus what it is now, divide by what it was, and then we get a proportion reduction in U0 variance specifically as our effect size. All right, how are we doing? So yeah, it's more complex, but there's nothing new in terms of concepts, really. This part looks a lot more like your standard linear model once you've gotten all the random effects built under it. Keeping track of which gets predicted by which is the tricky part. Any questions before we call it a week? No? All right, fair enough. Thanks for being here then. I will see everybody next week. Let me know if you need anything. You have a formative assessment that you should be able to do by Monday, and you also have homework 4 you can work on that's not due until a few weeks. So, see you all later.
Lisa,